Section 2. Active Earth. No matter how still we sit in our desks, our planet is always moving. Our Earth spins, rotates, cracks, and shifts all over the place. Without these actions, the Earth would be a pretty boring place. As you read this section, be sure to pay attention to the natural and physical processes of the Earth and how they can affect the people living here. Make sure you look for how does the rotation and revolution of the Earth affect us? What is the difference between climate and weather? Why is it cold at the North and South Poles? In what ways can wind become dangerous and destructive? What are plate tectonics? How do they affect the chain and change the Earth? What causes earthquakes? What happens if they occur underwater? In what ways is the Earth's surface naturally built up? And in what ways is the Earth's surface naturally worn down? It all revolves around the sun, day and night. The source of all energy on Earth is the sun. Without it, there would be no day and night and no seasons. Life could not exist on this planet without the sun. A flashlight aimed at a tennis ball sums up the relationship between the sun and the Earth. When the light, the sun, shines on the side of the tennis ball, the Earth, the other side of the ball is dark. Therefore, half the Earth is always illuminated and half the Earth is always dark. The Earth constantly rotates, so one side isn't always light or dark. This 24-hour spin causes our day and night cycle. As the Earth rotates or spins, causing day and night, it also revolves or orbits around the sun. Because the Earth's axis is inclined or tilted at 23.5 degrees, sometimes the northern hemisphere tilts toward the sun in June, and sometimes the southern hemisphere does in December. The hemisphere tilted towards the sun experiences summer, and the hemisphere tilted away from the sun experiences winter. The Earth's tilt causes one hemisphere to experience more sunlight or less sunlight at any given time of the year, which causes summer days to be longer and winter days to be shorter. As a result, the North Pole experiences total darkness in December, while the South Pole is in total sunlight, the opposite in June. Considering climate. Although people usually use the terms weather and climate interchangeably, they mean different things. Weather refers to the here and the now. It is the temperature, wind, moisture of a specific place at a specific time. Weather is localized, and it can be unpredictable. A good example of weather would be what it's like out today. If it's warm, sunny, and dry, that would be an example of the weather of a place, what it's like at one time at one specific place. Climate refers to the long term, or to average weather conditions over an extended period for a large region of the Earth. The world can be divided into many different climate zones that correspond roughly to their distance from the equator. Other factors such as altitude, proximity to a large body of water also play a role in determining climate. So an example of climate would be Michigan has a cold and snowy climate in the winter. That describes a larger place over a larger period of time. Why is it hot at the equator and the poles? The Earth is hottest at the point where the sun's rays strike it most directly. At the equator, the sun is always close to being directly overhead. At the North and South Poles, the sun is never directly overhead. During the Arctic and Antarctic winter months, the sun does not even appear. Even at the height of the polar summer, the sun remains close to the horizon. The air temperature is caused only indirectly by the sun's rays. The air is actually heated by a process called re-radiation. As the sun's rays penetrate the Earth's atmosphere and strike the Earth's surface, the surface absorbs the light energy from the sun and changes into heat energy that warms the air. Because some surfaces are more effective than others at absorbing and radiating heat, the Earth has varying air temperatures across the globe. The best absorbers of the sun's energy, and hence the warmer areas, are the vast oceans and the dark surfaces, such as asphalt, soil, and leaves. Smooth and light-colored surfaces, such as ice and snow, are less effective in absorbing energy from the sun and cause cooler temperatures. Why does the wind blow? The wind blows because of differing air pressures at various locations at the same time, which is caused by the differing temperatures and moisture content of the air in different places. Because water molecules are less massive than gas molecules in the air, increased water vapor results in decreased atmospheric pressure. In addition, cold air is more compressed and contains more molecules per cubic inch, so it is heavier than warm air and yields higher atmospheric pressures. Elevation, or how high you are in the atmosphere, also plays part in wind formation. At the sea level, the weight of the atmosphere is about 14.7 pounds on every square inch. The higher you go from sea level, as in up a mountain, the less pressure is exerted by the atmosphere. Winds are caused when heavier, high-pressure air pushes into areas of warmer, lighter air. All things in nature seek balance, so the winds are nature's way of equalizing the pressure of the atmosphere. The greater the difference in pressure and temperature, the faster and stronger the wind blows. Extreme differences in air pressure result in tornadoes and hurricanes. They call the wind many things. Twisters, tornadoes, and whirlwinds all refer to isolated points of extreme low pressure, warm, moist air, surrounded by rapidly spinning columns of wind. Although these roaring, funnel-shaped vortexes are not generally more than a couple of 100 yards wide, they leave terrible destruction in their path when they touch down on the ground surface. They may attain a wind speed of 300 miles per hour, but are more commonly in the 110 to 200 mile per hour range. The most tornado-prone area in the world is the Central Plains of the United States, or Tornado Alley. Waterspouts and dust devils are miniature and often short-lived versions of tornadoes. Waterspouts are misty columns of spray over bodies of water. Dust devils are similar, except that they occur over land. Hurricanes and typhoons are several tropical storms with sustained winds of 74 miles per hour or higher. These massive circular or oval-shaped storms can measure more than 300 miles across. A peculiar characteristic of these storms is their eye, the area of calm, often complete with blue sky directly in the center of the storm. They are associated with extreme low pressure. Hurricanes are storms that appear in North or Central America. Typhoons occur in the western portions of the Pacific Ocean. These intense rains and ocean storms, surges associated with these storms can inflict horrific damage, such as that from Hurricane Katrina and the New Orleans flooding of 2005. Cyclone is an umbrella term for all of the storms mentioned in this list, except for monsoons. Even low-pressure centers that do not develop into these types of severe storms are considered cyclones. The term tropical cyclone is also used more specifically to describe the Indian Ocean equivalent of the hurricane or typhoon. Monsoons differ from the other weather phenomena in that they're not a particular type of storm. Instead, the term refers to a seasonal shifting of winds. Although generally associated with southern Asia, monsoonal climates are also found in northern Australia, western Africa, and other parts of the world. Monsoons may be wet or dry. The wet summer phase of the Indian Ocean monsoon lasts from June to September and often brings torrential rains. Typical of this phenomenon is the 37.1 inches of rainfall on Mumbai, India, in a single day on July 2006. Or 26, 2005. The Earth's moving surface. It's not solid ground. Our Earth's surface, although it appears to be solid, is really the equivalent of many giant rafts of moving, bumping around on an orb of molten material while floating around in space. 225 million years ago, all the continents were part of a supercontinent called Pangaea. About 180 million years ago, Pangaea began to split up. Its parts slowly drifted away from, and in some cases towards, each other. The process, called continental drift, still continues. The Earth's surface, both the land masses and ocean floor, is made up of giant plates, or solid chunks, which is explained in the theory of plate tectonics. Floating and colliding continents. According to the theory of plate tectonics, the Earth's outer shell, called the lithosphere, is not continuous, but instead is divided into irregularly shaped rigid plates that float on an underlying molten layer called the asthenosphere. The plates move relative to each other at rates of as much as several inches a year, and they meet in a number of different ways. At divergent boundaries, adjacent plates are actually forced apart by molten matter rising up from the asthenosphere to form ocean floor ridges. The Mid-Atlantic Ridge, which splits nearly the entire Atlantic floor in half north to south, is a good example of divergent plate boundary. When plates collide at what is called convergent boundaries, the older, heavier plate is forced to sink below the lighter, younger one, often forming deep ocean trenches. This process is known as subduction. The colliding plates are carrying continents that also bang up against each other. The result is new mountain formation at the edge of the lighter, younger plate. The Himalayas, for example, are a result of the collision between the Eurasian plate and the Indo-Eurasian plate. Tectonic plates also meet at transform boundaries. In this case, the plates don't collide head-to-head, but rather grind sideways against each other, creating lateral faults and earthquakes. All of this plate movement generates tremendous amounts of energy, which is released in part through volcanoes and earthquakes. In fact, most of the world's volcanic and seismic activity occurs along plate boundaries and subduction zones. The most volatile of these zones is the perimeter of the Pacific Ocean. The infamous Ring of Fire, where the Pacific Plate is disappearing into deep subduction trenches. More than 75% of the world's volcanoes are located here. Among them, such celebrities as Mount Fuji, Mount Pinatubo, Kilayu, and Mount St. Helens. The Great Shake, earthquakes and faults. The activity along plates can cause tremendous pressure to build up. In an earthquake, a sudden release of energy causes the rock on one side of the fault to slip rapidly past the other, with either an up-down, vertical, or sideways motion. The wave vibrations generated by an earthquake are measured by a device called a seismograph. There are several ways to express the severity of an earthquake. The most common is the Richter scale, a logarithmic scale in which every whole number increase represents a 10-fold increase in earthquake magnitude. A 7 on the Richter scale, for example, represents an earthquake 10 times as powerful as a 6. An earthquake's destructiveness in terms of loss of life and property damage depends on its magnitude and the degree to which the area around the earthquake's epicenter is populated. By the time an earthquake hits a 7 or an 8 on the Richter scale, the damage can be catastrophic. A 9 on the scale has never been recorded. An earthquake of that magnitude would result in virtually total destruction. Earthquakes that occur undersea can generate destructive ocean waves called tsunamis. Although tsunamis are sometimes called tidal waves, this is inaccurate because this type of destructive activity has nothing to do with tides. The tsunami is barely noticeable on the ocean's surface. However, once these fast-moving waves reach the shallow water of shoreline, they build up to enormous heights and can cause extensive coastal damage. This is what happened in Japan last year that devastated all those nuclear reactors and caused so many problems. On December 26, 2004, almost a 9.0 magnitude earthquake off the west coast of Indonesian island of Sumatra erupted with a force equivalent to 23,000 Hiroshima-type atomic bombs. This violent undersea quake set water racing with the speed of a jet plane across the Indian Ocean. A wall of destructive water hit 11 countries in Southeast Asia with 150,000 people killed or missing and many millions homeless. Building up the Earth's surface. The movement of tectonic plates is also one of the Earth's land-building mechanisms. As the continental plates press against one another, the Earth crust folds, warps, and faults. The process of building up major features of the Earth's surface through movement and deformation of crustal plates is called diastromorphism. Another primary land-building force is volcanism, which occurs most commonly along the fractured edges of continental plates. Magma, or molten rock, is forced up through the cracks of the Earth's crust to emerge at the Earth's surface as lava. The buildup of lava and ash forms the familiar volcanic cones that soar majestically on the landscape, wearing down the Earth's surface. Weathering, erosion, and other gradual forces combine to wear away, in time, even the highest mountains. Prying plant roots and the freeze-thaw cycle eventually reduce huge rocks to small stones. Acid and rust chemically break down the Earth's minerals. The wind sculpts sand dunes, while wind-borne abrasives rasp away at exposed rock surfaces. But all of the agents of erosion at work in the world, the most powerful by far is water. Water erodes, wears down, and carves the Earth's surface in a variety of ways. Rain tides, flooding, and even ocean waves lapping against rock cause the breaking down and moving surface of water. Water also moves around great quantities of material. Streams typically originate in steep highlands and mountain areas. As they flow downward, the quickly moving water is capable of moving stones, sands, and silt. When fast-moving streams and rivers reach the lower, flatter land, the flow begins to slow. The slower moving water then spreads out to form floodplains, the wide, level valleys that store excess water when the river floods. As these streams and rivers reach the sea, they deposit their loads to form deltas. Deltas are characterized by rich alluvial soil, renewed by continual deposits of silt carried by the river from the land's interior. The crushing effects of ice. Water can also carve away effectively at the Earth's crust in another form, ice. Many landforms in the northern hemisphere are a result of glaciation. During the ice ages, the last of which occurred between 8,000 and 15,000 years ago, huge sheets of ice spread southward from the North Pole. These massive 10,000-foot thick glaciers scoured the land surface and left glacial lakes and deposits in their wake. The remnants of these continental glaciers are still found today on the island of Greenland and the continent of Antarctica. Smaller glaciers, called alpine glaciers, are also found in high mountain areas. Alpine glaciers advance and retreat seasonally, grinding the mountain rock into coarse till and fine material dust called glacial flour that cause the spectacular aqua blue hues of many mountain lakes. The least you need to know from this section. The Earth's rotation on its axis every 24 hours causes day and night. The Earth's revolution around the sun once a year and the tilt of its axis causes the changing of the season. The Earth is hottest at the equator because that's where the sun's rays strike the most directly, and it is coldest because they get the least direct sun. The Earth's crust is made up of slowly moving plates that grind and bump, and the Earth's surface is built up by folding and warping and volcanoes, and it's worn down by running water and ice.